Hey everybody, Mr. Lowry here. I wanted to give you some resources to help you get started on your homework. And so I picked out a few problems that I'm going to run through. Now this is your homework assignment for tonight. Okay, I'm going to do 4 of these. I'm going to do 4, 19, 26, and 40, which will kind of give you a little bit of a head start on each of those sections, or at least give you an example from one of those sections. Before we get through that, excuse me, before we get into that, there's a couple key concepts you're going to need to know from today's section, or from 10.1. Okay, the first one that I wanted, and I'm just going to go over these real quickly because I already did this in a video. But the first thing I wanted to talk about was, probability. We talked about it's a quantitative measurement of how likely it is for an event to occur. And it's a number between 0 and 1. What that means is we're talking about 1 is like 100% likely, and 0 is 0% likely. So if something's going to happen, it either happens or it doesn't, right? The most, like the biggest probability you can have is 1, which represents 100% as a percent. So if something is for sure going to happen, there's a 100% likelihood that it's going to happen, which means the probability is 1 if you write it as, like a fraction or a decimal or whatever. Okay, so 0 then, of course, would be 0%, and that's like nothing's going to happen. Like there's a 0% probability that this is going to happen. That means it's not going to happen. But you can also express it as a fraction, decimal, or percent. Now in your homework, most of the answers in the back of the book are going to be fractions, but then kind of towards the end in numbers 40 through 43, I think they do them as percents. So if you see something like 25%, keep in mind that that's 0.25, which is still a number between 0 and 1. So although this looks like it's a lot bigger than 1, 25% means 25 per 100. Okay, so it's somewhere in between never going to happen and for sure going to happen. There's a probability in there. Okay, another super important definition is sample space, which is a set or a list of all possible outcomes. Now in your book, it says all possible outcomes for an event. I said all possible outcomes for a trial, like if we're doing an experiment. The reason why it's kind of weird if it says event is because we use event sometimes as like a specific outcome. And so I didn't want to put event here because the sample space is not the specific outcome we're looking for. It's any possible outcome that could happen in that situation. Okay, so I'm just going to leave this blank. I think that's a better way to put it. So it's the set of all possible outcomes for whatever is going on. Now an event, usually we refer to that as a specific outcome that we're looking for. Okay, so sample space, it's a list of outcomes. Now theoretical probability formula is going to be really important, and that has kind of a sample space idea in it. To find a theoretical probability, it's the number of outcomes that match A, right? This is the probability of some event we're calling A. So the number of outcomes that match what we're looking for, or in other words, the number of ways that A could occur, is what I said in the video. In your book, the language is, I think, kind of weird. It says, let's see what it says. Sorry, I gotta flip the page back. In your book, it says number of outcomes in event A, which I think is kind of a weird way to say it. But basically the idea is it's the number of ways that A can happen, or the number of outcomes that you could possibly get that match that event A that you want. So basically what you want, divided by all the possible outcomes in the sample space, the number of all the possible outcomes. Okay, so that's how you find a theoretical probability, which we were going to do a lot on this assignment. The fundamental counting principle is basically if 2 things are occurring, you multiply the different possibilities together to get all the total possibilities. So if there's n ways for event 1 to occur and there's n ways for event 2 to occur, then there's m times n ways for both to occur. That's the fundamental counting principle. And we use this to make tree diagrams, and we use this to like do code words or codes with like letters and numbers. We use it to determine how many different like combinations of things there are. So that's kind of an important one. All right, so that's kind of the gist of it. You need to know those things. Those are the key concepts for today, for this homework. Okay, let's take a look at number 4, and I'm just going to read these to you because I don't have like, I don't have a regular book. I only have my, like, instructor's version, which has all the answers in it. So if I gave you that, I think you may not, that may be too easy for you if I gave you all the answers. So number 4 says this: find the probability of randomly selecting a red marble in one draw from a bag of 5 blue marbles, 3 red marbles, and 1 white marble. So you have 5 blue in this bag. You have 3 red, and then you have 1 white. Okay. So we're kind of assuming that like there's 5 different ways to draw a blue marble because there's 5 of them. We're also assuming that drawing one of these marbles is equally likely as any of the other ones. So it's not like you're more likely to draw one of them. They're basically all the same size. You mix them up real good. So there's randomness here, which is important. So if we want the probability of drawing a red marble, what we want is basically the probability of red. Okay? Well, going by our formula here, the probability of red is the number of outcomes that match red. Well, there's 3 red marbles, so you could draw, red 1 or red 2 or red 3. There's 3 different ways to draw a red marble because there's 3 red marbles in there, right? There's 3 outcomes that match pulling out a red marble. And then over the number of outcomes in the sample space. So the sample space is the set of all possible outcomes. So it's white, red 1, red 2, red 3, blue 1, blue 2, blue 3, blue 4, blue 5. Right, there's 5 different blue marbles and 3 different red ones. So if you add all those up, there's 9 in total. 9 total different outcomes that you could have. So the number of outcomes in the sample space is 9. So remember, a sample space is a list. The number of outcomes in the sample space is a number. We're going to simplify this to 1/3. Okay, so that's the probability. You have a 1 in 3 chance of pulling a red marble out of this bag. Most of the probabilities in this assignment are going to be in fraction form. It's not wrong if you put it into decimal. Of course, 1/3 you're going to have to round, so that's not as exact. Right? 0.33, 333, which would also be approximately 33%. Right? This is the most exact in this case, so that's probably what they're going to use most of the time. So keep your probabilities in fractions so that you can match the answers in the back of the book. Okay, the next one we're going to look at is 19. It's also going to be calculating a theoretical probability. Okay, so number 19, the wording on this section is kind of weird, so I wanted to go over that. It says calculate the probability of each event for one roll of a number cube. Well, what the heck is a number cube? They're talking about rolling a die. Now this is kind of weird because usually we say roll the dice because dice is plural, right? One die, or like singular for dice, is just die, just one. So when we talk about a number cube, we're talking about a 6-sided die. So the outcomes that you're talking about here are like 1 through 6, right? There's 6 different options. That's kind of what we're assuming. So the sample space, all the possible options that you could get from rolling a 6-sided, regular die is you can get 1, 2, 3, 4, 5, or 6. That's the sample space. So the size of the sample space, or the number of outcomes in the sample space, is 6. There's 6 different outcomes you could get there. Okay, and in 19 specifically, we want the probability of getting a number less than 6. Okay, so the probability of, we'll use a symbol here. We'll go probability of less than 6 is equal to the number of ways that we can get something less than 6, or the number of outcomes that match less than 6. So which outcomes apply? 5, 4, 3, 2, 1, all of those are less than 6. 6 is not less than 6. So there's 5 outcomes that match the criteria less than 6 out of the 6 total outcomes that you could possibly get. Okay, so that's your probability. It's just 5 out of 6. Now, again, if you wanted to, you could change it into a decimal. Of course, I wouldn't do that in this case just because you're going to get something that keeps going forever. So you'd have to round this. It's 3333. It's 0.8333333. So this is not quite as accurate as this fraction because this has to be rounded and this is exact. But that's about 83%, a little bit more. So this is what I would do. Okay, so again, that's just using your theoretical probability formula, which is not hard. It's just, I think the wording in the book is a little bit weird. But yeah, this is just the number of outcomes that match A, or the number of ways there are for A to occur over the total number of outcomes for whatever you're doing. Okay. All right, let's take a look at the next one here, which is going to be number 26. Okay. And in 26, it says, we're doing codes here, so we're going to use the fundamental counting principle. 26 says, or the directions for 26 through 29, find the number of possible passwords with no letters or digits excluded for each of the following conditions. So 26 is 2 digits, followed by 3 letters, followed by 1 digit. So 2 digits, 3 letters, and then 1 digit. So digit, digit, and letters. And we're not excluding anything. So there's actually only 10 digits, 0 through 9. After that, you get into like double digits, right? Like 10, 12, 13. So just for a digit, there's only 10 different, digits that we have. So the idea here is we have these different events. And the first event is just picking the first number in your code. How many different ways are there for that to happen? So if we're picking a digit, there's 10 different ways for that to happen. Now this is not saying that the first digit of your code is 10. What this is saying is there's 10 possibilities of getting there. It could be a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, so 10 ways for that to happen. There's also 10 ways for us to pick the second digit. So that's the second event, is picking the second digit. Okay, the fundamental counting principle only talks about 2 events, but we can extend it, and it keeps going. So the idea is, well, what if there's a third event? Okay, well, it's just the probability, or it's the number of ways for the event 1 to occur, times the number of outcomes for event 2, times the number of outcomes for event 3. And you just keep on going down the chain. So how many ways are there to choose a letter? Well, there's 26 letters in the alphabet. Okay. Event 4 is picking the 4th digit, and there's 26 possibilities there. The 5th event is picking another letter, which is, there's 26 options there. And then the last event, the 6th event, would be picking another digit. Okay, so we're just going to multiply all these numbers together to figure out, how many different options there are. So let's do that. 10 times 10 times 26 times 26 times 26 times 10. Okay, so 1, 7, 5, 7, 6, 0, 0, 0. We'll put some commas in here so we can read it better. So it looks like about 17 million. A little, maybe closer to 18 million, but yeah, that's a lot. So that's kind of how you set up those problems here. If you're making a code or whatever, think of choosing each piece of the code as an event, and then you multiply how many different ways there are for that event to happen. Okay, the last one I want to look at is 40, which uses a table. There's actually 4 questions that are like this. I'm just going to do one with you so you can kind of get started. Okay, so let me read it to you. It says, the table at the right shows the 1993 college enrollment statistics in thousands for the United States. Based on this data, find the probability that a randomly selected person enrolled in college in the United States in 1993 is in the given age group. Okay, and then number 40 is 18 through 24. So what we're looking for is probability that we picked somebody from this group, this college group. So we're assuming that they're in college. But what we want to see is if we picked from this group of all these people that are in college, what's the probability that we got somebody in this age range? Okay. So what we need to do is how many different ways are there to pick somebody in this age group? Okay. So if you look at the table, you have the 18 through 29 bracket, male and female. You have the 20 through 21 bracket, male and female. And you have the 22 through 24 bracket, 1260 for male and 1263 for female. So if you add all those numbers up, that's how many people you could potentially pick that are in this age group. That's how many of the outcomes, the possible outcomes, match your criteria, right? You want somebody in this age bracket. Well, add all those numbers up. So on top, we're going to have the 1224 plus the 1416 plus the 1294 plus 1414 plus, we got two more here, 1260 and then 1263. Okay, so that's all these. This is the number of males 18 through 19, the number of females 18 through 19, the number of males 20 through 21, the number of females 20 through 21, the number of males 20 through 24, and the number of females 20 through 24. So anybody that I pick from this group will match my criteria of that they're 18 through 24. And if I add these up, I get how many of the students match those criteria. Okay, now the bottom is all the possible outcomes, okay, for this situation. Now that means all the students in this entire table. So we're not trying to figure out the probability that somebody we pick is in college. That's because we don't have the full number of the people in the United States. What we're trying to figure out is what is the probability that if they're already in college, that we pick somebody in this age group. And so what we want for the bottom is all the different possibilities, all the different ways there are, or the number of ways there are, to pick somebody who's in college. Okay, so for that, we have to add up all the numbers in the whole table, minus the ages, every number in the male and female column. So if you're watching this, you're psyched because I'm just going to give you a huge hint. The total number of students in that table is this. Okay, now let's just pause for a minute to talk about the unit. Now this says this is in thousands, right? So this really, I should have like a 0, 0, 0. I should add a 0, 0, 0 to every single one of these numbers because it's not really 1,224. It's 1,224,000. That's how many people. But it doesn't actually matter because if this is in the thousands up here and this is in the thousands here, when I divide to get my percentage, since they're both in thousands, it's all gonna work out. It doesn't really matter. Okay, so let's add up the top numbers here and see what we get. Okay, so 1224 plus 1416 plus 1294 plus 1414 plus 1260 plus 1263. Okay, so that's the number of ways there are. That's how many students there are in this bracket. Now, of course, this is in thousands, right? So it's actually 7,871,000. But we don't have to worry about that, like I said. So this is, how many students are in this age range. So if I'm picking a random college student, I could pick any one of those 7,871,000 students, and that would work. Okay, now on the bottom, this is the total in thousands again. So there's 14,308,000, right? Thousand. So this is actually 14,308,000. But again, since this is in thousands, this is in thousands, when we divide, those units will cancel, and we're just going to end up with a percent anyway. So let's divide that number that we got by 14,308. And in this one, this isn't going to simplify very well, and so they put this in a decimal or a percent. I think they put it in a percent. So it's approximately 55% of all the college students in the nation for 1993 were in that age range, 18 through 24. Okay, so that's how you're going to set those up, and you're going to need this number for all of those because you're going to have the probability of some age range out of the total, and this is the total amount for that table, the total amount of college students in the U.S. in 1993. Again, this is in thousands. So 55% is what you're looking for there, and that will help you get the other three for that section. I think that should be good to help you get going. If you get stuck, then you're welcome to shoot me an email or something like that. But that'll help you get going, and this is the full assignment. Okay, so jump in there, do it on a separate sheet of paper, and upload that because I'm not gonna make a worksheet for you. It's gonna come out of the book. But when you upload your homework, please make sure that you hit mark as done. Otherwise, it'll still look at like missing. So when you upload your pictures, you gotta hit mark as done. Anyway, thanks. I hope that helps, and I'll talk to you guys soon.